Hello, it's Keith here, and this is the second of the ChibiAkumas programming tutorials. In these tutorials we're looking at the ChibiAkumas code. I'm showing you how it works and how to change it to make the game do something of your own, because as I've said many times, ChibiAkumas is open source and I completely encourage you to download that source and use parts or all of it in your own projects, whether they're just for fun or commercial. So just go ahead and use my code in any way that helps you. So last week we had a look at the coordinate system that the ChibiAkumas game internally uses, and essentially it's 160 units across and 200 units down on the visible screen with a 24 unit border on all sides of invisible area for sprite clipping. Now that we know how coordinates work within the game, we want to discuss how movement occurs, because once you've got an object with a position and a movement, you've got a bullet or an enemy or background object or whatever. So that's what we're going to discuss this week. As I said last time, everything in ChibiAkumas has to work with single bytes and values from 0 to 255, and the main reason for that is that memory and processing power are very limited. So in the same way as last time, all of the movements, whether a bullet or an object, are defined by a single byte with a value of 0 to 255. So let's discuss how the movements occur. Well, essentially all movements work the same, but there is a slight extra limitation added to bullets because non-bullets can have an extra special movement type. But we'll start by discussing the basic movements. So every movement will have a direction and a speed, and essentially it works on a grid where the movement direction on the x-coordinate can be -4 to +3, and the movement direction on the y-coordinate can be -4 to +3. And so obviously this is a 3-bit signed number. And so essentially the basic movements, as they're called, are defined by 6 bits. And the reason it's 6 bits is because the top bit is always 0. That defines a basic movement. The bottom 3 bits are the x movement speed, the next 3 bits are the y movement speed, and then the 6th bit is the double speed bit. And when this is enabled, it effectively speeds up the movement. And so if we represent the respective numbers of these bits on a grid, you end up with this design here. Now 24 is stationary, as would be 64, because a double speed of stationary is still nothing. So if we look at 1C, that would mean we're moving up slowly. 14 would be moving up slightly faster, and 0C would be faster again, and 44 would be the fastest up movement here. So essentially we've got this pattern here, and so we can do diagonals and linear movements, and diagonals and down and backwards and so on and so forth. And if we add 64 or hexadecimal 40 to one of these values, we end up with the faster version on this graphic here. So if you look at this, and if you've played the ChibiAkumas game, you may notice that when the bullet explosions occur, there's kind of a limitation to how many bullets will appear and what speeds they move, and it's this that is putting that limitation in place. To be honest though, generally speaking, although there is a sort of quite heavy restriction in this sense, it's not too bad. And this pattern was designed around the very limited amounts of memory, but also the very limited amounts of processing power for actually calculating the moves of the bullets. And we're going to have a look at the code in just a moment. Now, this is what values from 0 to 127 for the movement do. But there are the advanced movements. Now these aren't available for bullets, they're just available for objects, and they allow much more complex movements. So the first kind of movement is a background object, and you can see here this is when the top 4 bits are 1100, with the remaining 4 bits being the parameter of the speed. What the background objects are, they're very, very slow moving objects. So the slowest movement on here would be 23, but that's much, much faster than the slowest movement of a background object. And you can see this if you look at the gravestones and things in the level 1 of ChibiAkumas. You'll see the gravestones move fairly slowly, but behind that the castle moves even slower still. So that's what this first background movement, advanced movement, does. Now beyond that, we've got 3 seeker movements. Essentially, this is a bit of a trick. Whenever a seeking object is created, it's defined as this seeker object here, with the top bits as 10010, but then as soon as it comes into play, it will lock onto one of the players who are living, because the game engine won't know until that point how many players are alive, and it will pick the next one that is available. So if only player 1 is alive, it will always pick player 1. But if player 1 and player 2 are alive, the first one will seek onto player 1 and the second one will seek onto player 2 and then back onto player 1. And this is used by, firstly, the coins, because the coins are object in the game. So if a smart bomb is used, half the coins will fly towards player 1 and half will fly towards player 2. And that's what does this. But also the Zombie Chew character, who fires kisses at the players. The first kiss that's fired will seek on to player 1, and the second one will seek on to player 2 if player 2 is alive. So that's how those work. Now the next object is called the wave. Its bit mask is 1010. Originally this would create a wave type movement in a kind of sine wave pattern. This is used in ChibiAkumas episode 1, however it's no longer needed. ChibiAkumas episode 2 and version 1.666 had a much more advanced function called animators, which used an extra byte and a short script to define very complex movements. This function was available in ChibiAkumas episode 1.666 for backwards compatibility to make porting the game easier. However, it's now been removed from the new version of the game, which is the successor to Tragical Chase. I'm planning to call it ChibiAkumas versus the Z80 coding bugs. And this is going to be the heavily documented version of the game that we're going to be looking at in these tutorials. But for memory limitation reasons, I've had to take this function out because frankly, it no longer had any purpose anyway. Now beyond that we have 4 custom moves. What do these do? Well, they actually do nothing at all. They actually jump to the null routine, which just returns. The purpose of these is that a level program code can modify these and jump out of the main program loop that handles the drawing of the objects to run a special piece of custom level code that will redefine the object's position and movement dynamically and is completely exclusive to that program code. Now, this was used a lot in ChibiAkumas episode 1, and this is how things like the skull enemy worked and the jumping rabbit. But they were very hard to work with because they were literally assembly code and they were literally messing with the registers that the main loop expected to be working. A bug could crash the game very, very easily. And again, the animators can do almost everything that you could possibly want with this, but because they are essentially a scripting language, you've got a much easier programming path to get things working and a very low chance of a crash compared to the custom moves. So again, while they do exist in the program, and you may need to use them in very extreme cases, you should always look at the animators instead. And we will be looking at the animators in a later lesson, but they're just a little bit too complex at this stage. So that's the principle of the moves. So let's have a look at the actual source code and we'll discuss the actual code. So here is the do moves function here, and you can see there's just a general description of the movement definition byte here because a single byte will be passed into here. So the first thing we want to do is we check if bit 7 is set, because if it is, then we're using a special move, and if not, we're just using a regular basic move. So what we do here is we get the y coordinate, we rotate it to the right by 2 bits, and then we subtract 8, and this now gives us a value that we can add to our current position. Then we check the doubling bit, and if it's not set, we skip over this command here because this command will increase the size of the move. And then we've got some special code for the V9K, because on the V9K we need to be able to reprogram the core to make all of these move more slowly, because the V9K plus the Turbo is a very, very fast system, and so everything moves more slowly to compensate for the extra increase in speed. Now we add it to the current position, because of course this is a positive or negative value, and this will give the new position for the object, and we need to check if the Y position is off the bottom of the screen. And if it is, we go to this kill command, which will remove the object. Then we do the same for the X coordinate. We subtract 4 from it. We then double it if needed again, and then we add the current X position, and we check again if we're off screen, and if we are, then we kill the object. And how do we kill the object? Well, it's very simple. All we need to do is we set the Y coordinate to 0, because a Y coordinate of 1 is perfectly valid, but a Y coordinate of 0 means the object does not exist, and this is because the Y coordinate is loaded in from the arrays first, and so by checking if it's 0, it's a very quick way of skipping over objects that don't exist. Now, if we get to this point in the code, we're looking at our special functions where the top bit is always going to be 1. First, we check if we are actually doing any kind of special moves at all, because special moves don't want to run every single tick. Now you'll see here that we've got self-modifying code doing this kind of thing, and again this kind of thing comes in with the V9K again, because the special moves can't be easily slowed down, so we're actually skipping their operation every other frame to allow the slowdown without having to reprogram the complex code. Now you can see here actually most of the level specific moves are disabled here. The reason that I've disabled some of this code now in the new game, which was enabled in the version 1.666, is the Tragical Chase game, and now this new game, the ChibiAkumas versus the coding bugs, there was some extra code added to make the level more advanced and able to switch movement directions dynamically and repeatedly, and that made the core quite a lot bigger. The problem with this is I was literally down to about 9 bytes of remaining memory on the CPC Plus version, and so Tragical Chase has no CPC Plus sprites to compensate for this. With the Z80 coding bugs, we're back to the main Chibico character, and I wanted to bring those plus sprites back in because I've already drawn them basically, and because the game engine is much more the traditional ChibiAkumas game engine and not the Det Target game engine that Tragical Chase uses. So I wanted to find a few extra bytes of memory to be able to bring back the plus sprites but keep the extra clever code into the game core that the new level design needed. So this is one of the things that got removed, and I'll show you the other one in just a moment. So these two commands here are the level specific moves, and you can see they just jump to null, which does absolutely nothing. Now these would be modified by self-modifying code to jump to the specific module, so we don't need to worry about those. You can see here then we've got the 3 seeker objects, and we're going to see those in just a moment. So here's do seeker auto, and what this does is it checks if player 1 is alive or player 2 is alive, and it will pick a player accordingly. Now if both players are alive, it will pick a random player here, you see, and once it's picked the player, it flips the bits so that it picks the opposite player next time. Here we've got the code that's actually going to seek onto the player. So once we've selected a player, we need to match the speed to the original object, because coins move very fast, but the zombie Chukis moves very slowly, and deadly objects that target the player will have to move quite slow to give the player a chance to kill them. The coins move extremely fast. So we're copying the speed into the new object, and then we're ready to go again. Now when we want to seek onto the player, we're loading the data of the player, because this will allow us to get the position of the player. Then we are loading in the speed, and then we're using the R register because we need to make it slightly random. Because the if the speed is very fast, the object may actually miss the player and jump over the player one direction and over the player the other direction. So it doesn't always move the same speed, so eventually the coin will touch the player sooner or later, even if it bounces around a little bit first. It's very crude code here because for speed and memory limitations. So then what we're doing here is we are getting the player's Y coordinate, checking if the coordinate is lower or not, and moving in the correct direction to get closer to the player, and then doing the same for the X coordinate here. And this is how we get onto the player's position, because as I've said before, the player's position is in either player array for player 1 or player array 2 for player 2. So that's really all there is to it. Now I said just a moment ago that some of the code had been disabled here, but I actually needed to make up about 60 bytes of memory to be able to enable the plus bytes again on the new game, and so this wasn't the only thing I disabled. This was removed, the wave handler code was removed, but also I did some more optimization on the code I showed you last week, which is the text driver. And the main thing I've done here is I showed you last week there was a dividing routine for showing decimals on the screen, and at that point it was very basic, and it was using a division routine, and there was one for the hundreds and one for the tens, and so I'm actually sharing the same one for both now here. And there's been some other tweaks as well. More use of the protect BC command, which it means more jumps but less duplication of these commands here, just to save a few bytes. When you're working in the memory limitations that ChibiAkumas does on the CPC Plus, saving 10 bytes is a miracle. Saving 1 byte is often worth it. So it's only in cases where speed is an extremely limiting factor I will do things that are a little bit less efficient. Like you will notice here I'm using a JP instead of a JR. This code is designed to be as fast as humanly possible. So normally I'd do a JR to save the 1 byte, but in this case I've intentionally done the JP and sacrificed that 1 byte. But anyway, so let's just compile again for the CPC and we'll have a look. Now you can see that the code is compiled here, and it's got to memory location 2FDA. Now I know that if the code goes up to 3000 here, that will actually start corrupting the sound effects, or rather the sound effects will start corrupting the core. So this has to go no higher than 2FFF. So I've got a few bytes here left to play with, and as I'm going along, if I see anything that I think I can optimize that's not going to take more memory, I'm doing it, because I still have some more plans for the current ChibiAkumas shoot-'em-up game engine before I start my next non-shooter game. You know, for me to write a whole new game engine and a whole new game is going to take months, could easily take a year or more. and so I want to try and make a few little fun games with the current game engine to give people some fun with the code I've already got, while I'm working on something much more adventurous. Because, as I say, working on a game for 6 months, 12 months, or even more, it's really hard morale-wise. So having a few little things to just throw out there and maybe have people have a bit of fun with them, that's much more rewarding in the short term, and it gives me a breather to get on with that big project in the future. So anyway, so that's the code there. Now let's have a look at how we can actually use this. So we're going to have a look at how to use these basic moves now. Now we can't really use a move on its own. Moves, as they are shown there, are used within the memory of the game's engine, but it's not something you can directly really poke in. But what we can do is we can jump a little bit ahead, and we can actually create an object within the game. So this is something called the event stream. The event stream is literally the level as a sequence of timed events. We're going to look at it in much more detail, but just for now we're going to cheat, and we're going to put an object at the very start of the level before this first new enemy batch command. Now this new enemy batch command is quite advanced. It uses a predefined set of enemies to create very complex levels of batches of enemies that will make a very, very large game very quickly and without multiple loads. So it's very advanced, but it's too advanced for today. So we're going to jump in before that, and we're going to create a command that occurs before its time. Now this event occurs at time number 6, and times will go from 0 to 255 and then roll back to 0. So there's no limit to the amount of times we can have. The only thing that matters is the events occur in sequence, and so we have to wait until the next one occurs. So I'm jumping in at number 10 here, and so this number 6 event here will have to wait nearly 255 ticks before it will ever happen. So we've kind of snuck in before it. And what we're doing here is we're going to have 3 commands at this time. So time 10 has 3 commands. The first one sets the animator to 0. They're too complex at this stage, so we're turning it off. Then we're going to define the program, the move, and the life. The program is nothing, which means it doesn't fire. This object won't fire at us. And then we're going to use move 23. 23 means it's going to move to the left. And the life is going to be 1, so it will take 1 shot before it dies. Now we're going to use a 2-frame sprite, and we're going to use sprite number 15. And here's sprite 15 here. So it's this little blobby guy. And it's a 2-frame sprite, and that means we're going to see both of the banks of animation here. The ChibiAkumas can support up to 4 banks, but we're only going to use 2 because we haven't defined more than that. Its position is going to be 24 plus 80 across. Now 24 is the invisible border, and 80 is basically halfway across the 160 unit wide screen. And then it's 150 down plus 24, so that's 2/3 of the way down the screen. And we had to put it there because we appear in the middle of the screen, so it would kill us immediately if we didn't do that. So that's that. And then what we're also going to do is we're going to enable the debug show level time, and this is a debugging tool for solving problems that happen in the event stream. So now we're going to compile our level, and then we're going to bring in our Amstrad CPC here and do run disk. We'll just fast forward the loading sequence, and there you can see is the blobby character, and it's moving across. But there's a problem. It's only got 1 frame of animation. This isn't a bug. The problem actually is I've got the Amstrad CPC set to 64K, because on the 64K system there isn't enough memory to use the second bank. So if I select 6128 plus with PowerDOS here, reboot the machine, run disk, and now we have the 2 frames of animation there, and you will have noticed we also had the loading screen. Now this is the work in progress of the new ChibiAkumas versus the coding bugs, but obviously things were a bit messed up. The title screens aren't changed yet, and I've got a lot more work to do, but you can see things are moving along a little bit. Now you can also see there's a number at the top of the screen, and it says on the right hand side 06, and on the left hand side there's a counter going up. The 2 digits on the left hand side are the current tick of the level, and the number on the right hand side is the next tick that is going to happen. So the next event is going to happen at tick 6, which is why you can see 06 on the left hand side. So if we fast forward the game until we go past FF to 06, now you can see that some more enemies are coming in. Well, what happened here? Well, what happened is this new enemy batch came in and started using our procedurally generated level enemies. So that's what this code would have done. And if I changed this to 7, you would see that that time on the right hand side would have been 7. If I changed it to 35, it would have happened at 35. And if I changed it to 15, well, we'll see in just a moment. So we just made an object move to the left. What happens if we want to make it run really fast diagonally? Well, let's try changing this to 0.9. Compile our game again. And let's run the game again and just see what it looks like now. And so there's the enemy coming in, and it's moving pretty fast now, and in fact it hit us. And you'll see now that the new enemies are coming in because of that new enemy batch much faster, because we then hit the 15 time. And you can see there's more times coming in as the next batch of enemies are coming in. And this is quite important, because if you're getting a crash and it's part of your level code, your first question will be, well, what time did that crash occur? Well, what enemy came in? Was it an enemy came off the screen and the sprites corrupt? Is it that I had a timed event that was jumping to a piece of code and crashing the game? So that's quite important. So you can see there that we can use any of these numbers, or even any of these numbers if we want faster movement, to get a movement in any linear direction. And of course, if we wanted a seeking object, we could do that too. So let's give our character some trouble here. Let's create a seeking object. And you can see the object is actually now chasing after us here, which is quite unpleasant, really. So there we go. You can see here I've been using these symbolic definitions, but I just use a binary definition here. Of course you can do either, but obviously for clarity it's better to use the named definitions. And you can see them all here in this event stream definition module here, and we will be going over all of this in much more detail later. So I wouldn't suggest you rush ahead, but if you're really chomping at the bit, then this is the kind of thing you would want to have a look at. And you can see we've even got directional definitions of these numeric ones, but often the numeric ones are actually easier. And you can see there's a text-based representation of those numeric definitions here. So just would use whatever you prefer, whatever makes you more comfortable. So we've had a look at this week at how the movements occur and how the program works with them, and how we can actually make those movements apply to an object that we create in the game. We're going to be continuing with this series, and I'm hoping I'm going to be able to show you everything about how the game works. And so even if you're a real beginner at game coding, I want you to be able to make your own enemies, put them into the game using my sprite editor, and then make those enemies move around so you can create yourself a fun little playable game with relatively little experience. Anyway, I hope you've enjoyed this week's lesson. If you did, then please like and subscribe, because that's a big help to me. And I hope you'll join me for next week's lesson. Thanks for watching, and goodbye.